Hello, this is just a recap of some of the material that we missed whenever we were going through our session. So the first thing that I wanted to talk about that we didn't get onto was dispersion. So here is the album cover of Pink Floyd's Dark Side of the Moon. It's pretty famous, and basically what's happening here is we've got a prism of glass. We've got pure white light hitting the prism. So as we talked about, whenever light hits a medium and it's going from our medium of air here to glass here, it's going from a less dense to a more dense medium. And thus the light will bend towards the normal. Okay, so we've got our incident ray here and our refracted ray here. Okay, so then if we look to this barrier, we've got our light coming in at this angle to our normal, and then it's going from a more dense to a less dense medium, and so it will move away. Now, pure light is made up of the colours of our rainbow. So the colours of the rainbow all have different frequencies, going from our low frequency to our high frequency, and the higher frequency light, such as violet and blue, will move away faster from the normal in our less dense medium than the lower frequencies of red and orange. And that's why we get dispersion. So it really should look a little bit more dispersed. So the red might be out here, the purple or the violet might be out here for a better diagram. And that's essentially what's happening. It's all to do with the speeds of the different wavelengths and frequencies of light. So that is dispersion. Total internal reflection, which we were talking about a bit, happens whenever the light is no longer refracted. So here we have our incident ray coming at this shape of glass. So it's a semicircular shape because the semicircle doesn't really refract the glass. Okay, so it hits our barrier and it's in glass and it's going to air. So it's going from more dense to a less dense medium, and therefore it's moving away from the normal. Okay, so you can see that here. If we have our barrier and our normal, our incident ray comes in at this angle and goes away at this angle. So it moves away from the normal. Okay, the angle there gets bigger. This is a reflected ray because there's always light reflected at the barrier. However, in this case, the reflected ray would be very, very weak. You maybe wouldn't even be able to see it with just your eye. So the greater the angle of refraction. Okay, so if we keep increasing this angle here of incidence, we will get to a certain point, the critical angle, and at that point the refracted ray is at 90 degrees to our barrier. Okay, our barrier here, and then sorry, not 90 degrees to our barrier, it's at 90 degrees to normal, and it is parallel with the barrier. Okay, so at this point this ray is the weak ray and the reflected ray becomes stronger. Okay, so the greater that you increase the angle of incidence, the greater the reflected ray will become. Okay, because more light is reflected. Beyond this angle, which is our critical angle, we get total internal reflection. Okay, so at this point the angle is too great for the light to be refracted. Okay, because it would be moving away from the normal, and to do so it would be moving into our glass block. Okay, so here the light is entirely reflected where the angle of incidence is equal to the angle of reflection. So this is used in industry, and it's used in industry in fiber optic cables. So I've drawn one here. So in a fiber optic cable, you've got a glass interior. So all of this here is glass. Okay, the outside of the glass is a cladding, and the cladding is of a more dense medium than the glass. Okay, so a less dense medium than the glass. So going from because if it were a more dense medium, if we look at this diagram here, it would be reflected towards the normal, and therefore there would be, refracted towards the normal, and therefore there would be refraction, which is why it has to be a less dense medium. Okay, so if we take the entrance to our fiber optic, we've got our normal here, our incident ray, and it sort of curves towards the normal. Okay, and at that point it will no longer refract at this barrier here, so it must have total internal reflection. Okay, so the light just sort of bounces the whole way along, and we get a light with the same coherent signal out the other end of the fiber optic. So that's total internal reflection, and that is how that works. Okay, lenses now. So there are two different types of lenses. There's the converging lens and the diverging lens. Okay, so the converging lens takes rays of light and converges them towards a point, a focal point. Okay, so here is a ray that is undeviated through the optical center. The optical center goes through the middle of the lens, and is right in the middle of the lens. So a ray there will not be converged. It'll not be refracted. It's straight through the optical center. It's the equivalent of going at a ray straight through the normal. Okay, that also won't refract because there's no angle for it to refract at. A ray at the edge of the converging lens, however, will be refracted and will converge towards a focal point. So converging lens in a lens diagram is drawn as such. Okay, and we draw our rays first of all parallel, always parallel, apart from the ray that is going from our image through the optical center. Okay, and hopefully we can talk about this a bit more in a further lesson. A diverging ray, diverging lens on the other hand, takes rays through the optical center and they diverge or they spread out as if they were coming from a point behind the lens. Okay, so they're refracting and they're refracting out the ways rather than in the ways. Okay, it's all to do with the shape of the lens. So it's quite useful in glasses. A converging lens is used for people with nearsightedness or short-sightedness, and a diverging lens is used for people with long-sightedness. So that's reading glasses. Okay, which brings us on to the electromagnetic spectrum. Okay, so there are different types of electromagnetic spectrum. I've got an image of it here, and it's all to do with the wavelength and the frequency. Okay, so as you go down in wavelength, you will go up in frequency, and that's all to do with the wave equation. Velocity is equal to frequency times the wavelength. V equals f times lambda, because this velocity is always the same. It's the speed of sound, which is 3 times 10 to the 8 meters per second. Okay, so as you go down in wavelength, you'll go up in frequency, and that's just to keep the same ratio between the two, so you get the same speed of sound. Okay, so at the very long wavelength, low frequency end, we've got radio waves. Then moving up in frequency, also up in wavelength in this case, we've got microwaves, down in wavelength, and then we've got infrared, visible light, ultraviolet light, X-rays, and gamma rays. So you need to know a bit about what these do. Radio waves we use for communication, walkie-talkies and radioing between, the air traffic control, for example, and the pilot. We use them in TV, and we also use them in FM radio. And because they're used the same, that's why you can tune your TV to a radio station. Microwaves we use in mobile phones. We also use them in satellites, GPS, and cooking. The water molecules absorb microwaves very readily, which is why it heats our food. But humans are also about 70% water, so microwaves pose a significant risk to our health. Infrared, all objects that are hot give off infrared. Okay, it's used in night vision. It's also used in remote controls. Visible light we use for sight. It's also used by plants in photosynthesis. Ultraviolet light is used for detecting forgeries, sort of black light. You can use it to show you can shine ultraviolet light at special inks that will only show up under that light. It also gives a sunburn. It comes from the sun. Anything that's really, really hot will emit ultraviolet waves. I think the temperature is something like 4,000 degrees Celsius. Anything above that there will emit UV light and will give you sunburn or even skin cancer. X-rays are used in medicine. They're used both for detecting different things in the body, sort of looking through and putting photographic film behind a bone. For example, if you put your arm in photographic film, the X-rays pass through your muscles and all the skin and stuff, and are reflected by the bones, which is why whenever we see it, we're able to see a sort of bony. I was going to draw a hand there, but you're able to see the reflection of the bone, and therefore we're able to see breaks and things like that there. It's also used in treatment. You can use it in radiotherapy and stuff, but you're far more likely to use gamma rays, although you can use X-rays. Gamma rays are really, really high frequency, high energy. They're used for cancer treatment, as I just said. You can also use it for detecting leaks in pipes, and you can also use it to kill surface bacteria in food. It's the same. These two are basically the same, using it to kill the surface bacteria and using it to treat cancer. It's just killing cells. This is used just to prolong shelf life and stuff. Okay, now we'll go over that in more detail on another day, but just for a quick, overview of what we missed there, that is that. Okay,